So in the previous video I just explained how using Solver we might estimate values in a linear relationship that minimize the error associated between generating a linear fit and a true value. If we were to use built-in functions available in Excel, so let's say we had this information again, copy, and we were to paste those in, so we could say paste special values. Okay, and we were to tackle the problem, what is the relationship between x and y, specifying that y is equal to some constant plus a coefficient called beta, or b times x, the independent variable. In Excel, one way of generating this relationship is to use the linest estimator. So we can say equal to linest, which is calling up, we can have a look at this, it's calling up a linear estimator, an OLS estimator. So the linest function calculates the statistic for a line by using least squares method to calculate a straight line that best fits your data, and then returns an array that describes the line. Okay, so the line here is, if you like, the fit that we would have seen in the previous worksheet. So we're trying to estimate the A and B that we would have observed before. So let's just set it out. Equal to y. The first input is an array. An array is a set of values, not just one value, but actually a set. And it's the dependent variable. And then x could be one or more arrays, but we just have one here. It's a single variable, single independent variable here. Do we want a constant? Well, previously we did have a constant, it was a, so we're going to say true, T-R-U-E. And do we want a set of complete statistics? And a set of complete statistics are, for instance, t-tests, r-squared, standard error. So okay, let's have a look at those. f-tests, true for those as well, and close. And if we hit return, we just get one value. Okay, so that's obviously not giving us all the information. In fact, what we're looking for is 2 and 3. That's what we're looking for the A and B estimates. So in order to generate that output, it's not a single value, it's an array, and we should think of the set of typical diagnostics that come along with the linest function. So we generally go across 2 if the relationship is y is equal to a plus b times x. We might go across 3 and then come down 4 or 5. Okay, so to generate this output, then we don't just hit return, we hit shift control return while having highlighted the number cells, right? And that space fills up. Of course, this array here, this is redundant, it's no significance, but what has significance is, remember we said the relationship between y and x can be described as y is equal to a plus b times x. The arrangement here, or the order of the values here, is the constant is reported last, and then b, the coefficient on the independent variable. And so we can see that the constant is 2 and b is equal to 3. Also the r squared, so okay, let's try to offer some kind of what does this output give us? Well, we have coefficient estimates. Okay, so that's the first row. Then we have standard error, and then we have r, the r squared, and with an r squared of 1 it implies there's absolutely no error. How would we work out the t-stats? The t-stats can be generated. The t-stats are used for constructing confidence intervals and for constructing estimates to what degree can we be confident that both 3 and 2 are not equal to 1. And generally the rule of thumb is so long as the coefficient divided by its standard error is greater than 2, right? So long as so let's run that again. So long as the coefficient divided by its standard error is greater than 2, and in this case it's enormous because this is a scientific term and we're looking at a number in excess of a billion. A billion is 9 zeros, 12 zeros, you know, so t-stats that are just stratospheric, enormous, right? And also for a very, very large t-stat of zillions, okay? Literally zillions. So we are absolutely confident that a and b are not equal to 0 using our conventional t-stat type test. And then in addition r, the r squared being the first value here, is also equal to 1, which means there is absolutely no error, which is quite rare. Now in a moment we'll look at we can take the same estimation again, just change some of the figures, we'll introduce error, and we'll look at what happens to our r squareds and our t-stats. Okay, so that's output, and that's linest, and linest is it can be used for single variable, multiple variable, linear regression. It's a very handy tool in Excel because it's very flexible. There is a more structured approach here to estimating the linear regression. We could go into the data, and if you have data analysis tool pack available, you can go data analysis. We can come to regression, so hit OK, and let's see what's our y input here. Our y input are these sets of values here. What's our x values? And do we want confidence intervals, labels? We might take those. We'll put into a new worksheet rather than an existing set of cells here. We might look at, okay, let's just go with that and see what happens. And this is our sheet 4. So this is from the data pack. This is from data analysis. And we can see, is there some kind of correspondence between what we have here, the sets of values that we have here, and what we got from the linear regression using linest. So with linear regression, let's just let's just have a look. First of all, the r squared is 1. Okay, so that's proof positive that we have the same as here. Secondly, the coefficients for A and B. So the constant, intercept is the constant, the coefficient for the constant, the estimate of the constant is equal to 2, and for y, I change this to y, is equal to 3. And we can take these values and have a little look, right, and copy and paste back in here. Let's see, home, and paste special values. Okay, and what we can see is, yes, 2 and 3, so we can think of A and B. We can think of the standard error. So if we represent it, let's take this and just widen it out a little bit. Now, there is a small difference, although at first glance it looks very substantial. But if we take A for the moment, let's take A. This is so infinitesimally small. Remember, it's scientific notation, so we're talking, we're looking at values and we're thinking in terms of 0.00000, and we go out maybe 14, 15 times, and then we get to 2, and likewise here infinitesimally small, but also while they're not exactly the same, they are infinitesimally small. And so the t-stats that we get, well, we can just verify if we take this value and we divide by this, we replicate the standard error. And if we take this value here, if we take the coefficient and divide by its standard error, right, we get the same values here. So these t-stats we can generate by taking the coefficient estimate, dividing by the standard error, but they're so huge and so in excess of 2 that we can say we're absolutely confident that A and B are not equal to 0. A is not equal to 0 and B is not equal to 0. So these t-stats are, if you like, tests that look at A in isolation and ask the question, is A equal to 0 or not? And the t-stats are so in excess of 2. 2 is normally, if we exceed 2, we're normally relatively confident that the value, the coefficient, is not equal to 0. Okay, and likewise here, if we find that B is in excess of 2, if the standard error is in excess of 2, we tend to dismiss the possibility, or we tend to be confident that that coefficient is not equal to 0 also. So we have very big values here for t-stats, and the probability of being equal to 0, the p-value, if you like, is the probability of being equal to 0, is tiny. Again, we have a negative power, so this is scientific notation, and we have a negative 10 to the power of 59 negative, so 10 to the power of negative 59 multiplied by this 10 to the power of negative 64 multiplied by this 8.1. So these are tiny values, tiny probabilities we're attributing to the possibility that A and then B are individually equal to 0. The confidence interval is tiny. We don't generate, so the could A be more than, less than 2, greater than 2? We work with tiny confidence intervals, mainly because, right, this is an exact relationship. Okay, so we'll see in a moment when we introduce error how this actually, how this analysis changes in terms of output and interpretation.